Good morning, everyone. My name is Anne Greenwood. I'm the Education and Training Lead for Population Data BC, and it's my pleasure to welcome you to our second session in our webinar series, The Power of Population Data Science. It's my pleasure to introduce Dr. James Doidge and Dr. Harvey Goldstein, who will be presenting on the future directions in probabilistic linkage. By way of introduction, Dr. Doidge is an epidemiologist based at the University of College of London, Great Ormond Street Institute of Child Health. James has worked with linked administrative data in Australia and the UK and advised the UK Office for National Statistics and NHS Digital on data linkage matters. He has taught courses on data linkage at several institutions around the UK through his work with the Administrative Data Research Network. His current interests focus on developing new methods for data linkage and analysis of linked data, which he applies to a diverse range of research topics in population health. Dr. Harvey Goldstein is a professor of social statistics at the University of Bristol and the University College London Institute of Child Health, as well as a visiting professor at the London School of Hygiene. He is currently a joint editor of the Journal of the Royal Statistical Society, Series A, and was awarded the RSS Guy Medal in Silver in 1998 and elected a Fellow of the British Academy in 1997. Dr. Goldstein recently authored a substantive reference text in the area of statistical data analysis entitled Multi-Level Statistical Models. His research interests include statistical modeling techniques in the construction and analysis of educational tests, with a particular interest in institutional and international comparisons. Dr. Goldstein's most recent work has focused on developing efficient methods for handling missing data and measurement errors in complex models, including multi-level ones, procedures for unbiased and efficient record linkage of large data sets, and procedures for maintaining data integrity while ensuring privacy in the release and analysis of big data sets. Before we get started, I'd just like to remind our audience that you can use the chat function on your GoToWebinar panel to ask questions, make comments as we go along. I'll be monitoring those questions, and near the end of the presentation, we'll open the floor to your questions and comments. If you have any difficulty using the chat function, you can also send me a direct email, which you have from the introduction, and I can respond that way as well. So without further ado, I'd like to pass it over to James to get started. Thank you.
Hello. Thank you for that introduction, Anne. So we're going to start off today by introducing some basic concepts in record linkage and talking about what probabilistic linkage is and what it isn't with respect to its main alternative, deterministic linkage. We're going to look at two sides of what are essentially the same coin in linkage. So that's the linkage step, where we make comparisons between records to try to identify whether they relate to the same person or entity, and the analysis step, where we use linked data to draw inference about the world. We're going to present, we've got a couple of our ideas for how we think that we might be able to do better in each of these steps in the linkage process, and then we'll finish by sort of reviewing some of the main lessons that we've learned from this. So, error and uncertainty in data linkage. The aim of record linkage is to identify unknown relationships between records. Usually this is whether or not two records relate to the same person, but it could also be whether they're the same family, or whether they're mother and son, whether it's the same company, or any entity. Really, it's any unobserved relationship between records. And the main source of information that we have to make these, to distinguish between matches and non-matches, is the pattern of agreement that two records exhibit over a set of matching variables. So these are usually things like name and address, dates of birth, sex, but they can be any characteristics that two records share, that have in common and that are actually observed. So if we take these two records as an example, then the pattern of agreement that they exhibit is agreement on first name, agreement on surname. The dates of birth disagree, but the gender is the same. So perhaps these are two records that truly do relate to me, or perhaps one is me and one is my father. Now, in terms of assessing agreement, rather than just binary agree, disagree, we might want to take a sort of more nuanced comparison. For example, by looking at these two dates of birth, we see that they're actually very similar. You know, maybe the day and month got swapped around, and maybe there was an error in the year of birth. So that we could assess that as sort of partial agreement rather than full disagreement, or binary agreement, disagree. Now there are two types of error that can be associated with linkage. If we put the link status, whether we decide that records really do relate to each other, in a 2x2 table against the match status, so whether they really do relate to the same person, then we have missed matches or missed links, and false matches or false links. So these are when two records really do relate to the same person but are not linked, that's a missed link, and when two records really don't relate to the same person but are linked anyway, then that's a false match. And from these 2x2 tables, we can develop measures of linkage error, the most common of which are recall and precision, which relate to sensitivity and positive predictive value, which you might be familiar with from other applications of 2x2 tables, for example, in diagnostic screening. Now, uncertainty in linkage arises from overlap in the patterns of agreement that are exhibited by matches, the true matches and the true non-matches. Usually it's the case that there are some patterns of agreement for which some of the record pairs that exhibit that pattern are matches and some are not. And no amount of fancy analytics can remove that uncertainty. And when we can't remove it, what we really want to do is measure it. So error and uncertainty are sort of two ways of thinking about the same thing. If we make a call and classify everything as a link or not a link, then we have errors in the data. But what we're going to introduce later are some ideas about how we don't necessarily need to make those final classifications and instead take information about the level of uncertainty associated with each pairs, which is reflected in something called the match probability. So match probabilities are almost equivalent to the concept of precision. So you can think about them as being the proportion of similar pairs that are matches. And when we're working in linkage applications that have one-to-one or one-to-many restrictions, so this is where only one link could possibly be true for the records in one or both files, then these restrictions introduce additional sort of limitations on match probabilities. So nearly all modern approaches to probabilistic linkage that are in practice are underpinned by a statistical model framework that was formalized by Fellegi and Sunter back in the 60s. It's based on measurements, these sort of key parameter inputs, which are called M and U values. So M values are the proportion of agreement among records that really are matches. And this captures information about the quality and consistency of matching variables. So variables that are not subject to change over time very often, like date of birth or gender, have high M values. And this feeds through into low match weights, low match probabilities when you have disagreement on those variables. Matching, on the other hand, you have some matching variables are much more unique. So people's social security numbers and NHS numbers, there are lots of different values that they can take, and they're quite specific to an individual. Matching variables like that have very low U values, which translate into high match weights, high match probabilities when you observe agreement on those variables. And these are then usually used to create log likelihood ratios that are summed over matching variables to produce a match weight, which is really just a score for every possible pattern of agreement. This summing over matching variables is something that's done to make the problem tractable, to make it sort of computationally feasible, but it's a simplification of the underlying theory, and it introduces an important assumption of independence between the matching variables, which is something we're going to talk about a lot today. So this assumption of independence between matching variables is sort of required for match weights to be able to be interpreted as any sort of match probability. But it's violated routinely in practice. So it's violated when matching variables naturally change together at the same time. So when you move house and you change your street, your house name, your house number, and your street name, and your postcode, and maybe your general practice, the places where you're registered, all these variables that might be used as matching variables, they all change at the same time, and that makes them dependent on each other. It's also violated when errors are introduced simultaneously. So, for example, when transposition errors are present in the data and the values of different matching variables are swapped around, and errors are introduced simultaneously across multiple matching variables. And it's also violated by natural correlations that occur between matching variables. So, for example, gender-specific first names. Records that agree on first name, you can be almost certain are going to agree on sex as well. And so having information about both of those matching variables doesn't necessarily tell you anything more. And lastly, the one-to-one and one-to-many restrictions that I mentioned earlier introduce additional constraints that cause dependencies between match probabilities. Now, these violations of the independence assumption, they can be a problem for ranking, but then they're not necessarily a problem for how we usually use probabilistic match weights, which we're going to get to, and which we're going to come back to in a moment. But they're definitely a problem for estimating match probabilities, which is usually done using Bayes' theorem. So let's talk a bit more about what probabilistic linkage is and what it isn't with respect to deterministic linkage. So this paper that was published last year in IJPDS, which you can find online, so it runs through 10 common myths and misconceptions about probabilistic linkage, and some of those are pretty nuanced, but we're just going to focus on sort of the essential myth that underlies a lot of those today and the ones that arise from it. So this is this idea that probabilistic linkage is based on the probability that a pair of records is a match. And from this, people often assume that it's different to deterministic linkage, that it's not as precise, that links identified using probabilistic linkage are not necessarily matches just because you've used probabilistic linkage. And these sort of myths and misconceptions all arise because of the idea that match weights are truly reflecting match probabilities. The key points that we wanted to take home from this paper was that for every pattern of agreement, there's a potential deterministic rule that could be used and a probabilistic match weight that can be calculated. But there are some things which probabilistic linkage can do that are very difficult to do in deterministic linkage. So particularly when it comes to using large numbers of matching variables, using value-specific or frequency-based weights, so where you might give a higher weight to agreement on rare values like my surname, Deutsch, versus more common values like Smith. And some measures of partial agreement. So the partial agreement between the dates that we mentioned before, or between two similar strings. But the main thing that probabilistic match weights provide is an indicator of the relative quality. So it's the relative quality of candidate links. And this is usually employed just to rank all the candidate links and then classify them by just selecting the best. And this classification, this employing thresholds and algorithms to identify the best links from probabilistic match weights, reduces the whole procedure to being fundamentally deterministic once more. And so later Harvey's going to introduce some ideas about how we can make sort of better use of that information about match weights without just necessarily classifying everything as definitely a link or not. So the other key point, just to reiterate, is that unless this independence condition between the matching variables is met, and you know these M and U values, and it can be quite difficult to know M values, then estimation of match probabilities requires additional information or assumptions. So match weights are not match probabilities. So I'm going to hand over to Harvey now to present the first of the alternatives to Fellegi and Sunter that we've come up with. So this is the paper for this was published at the beginning of last year in Statistics in Medicine, authored by Harvey Goldstein, Katie Harron, and Mario Cortina-Boyer.
Okay, thank you very much, James, and good day to everybody that's listening to us. So you'll probably pick up, James and I have different kind of emphases on this. We, differ in terms of what we think are the things that are important, but most things we agree on. So what I want to do is I want to have a little closer look at what James has introduced, the so-called Fellegi Sunter method, and there's a reference there to a paper that describes it. In addition to James's point about the independence or lack of independence between the different identifiers like date of birth, location, street name, and so on, there is a more fundamental problem with the model. The statistical model underlies this method. It's often known as a latent class model. And this has been pointed out by a few authors over the last 10 or 15 years, and that is that it's actually a misspecified statistical model. So the properties of the estimates that you get out are not what you think they are. They're not what the software tells you they are. And in that situation, that may well be a much more important limitation of the method than the simple lack of independence, which to some extent, at least in many cases, can be avoided by judiciously grouping the separate identifiers into composite identifiers. Now, I'm not going to go into that. There is a discussion of that in the paper that James referred to that was published last year. But the third bullet point here, I think, is the one I want to emphasize, that if you're going to use this algorithm, the FS algorithm, you can use it as a convenient way of getting scores or weights, but it doesn't have typically the claimed properties for it that we used to. One. Okay, so that's where we start. And I have to say before, let me preface this discussion by saying that I think although it is important to establish how you derive these weights where you don't have complete agreement or complete disagreement, so somewhere between 0 and 1, if you like, although that's important, it's not the most important issue in so-called probabilistic linkage. In fact, let me go further and say I think the term probabilistic linkage is a misnomer. And James referred to this when he said that what many people, if not most people, do is they take the series of weights and they choose a threshold, and above that threshold, a pair that has a weight above that threshold is regarded as a true match, and below the threshold as not. That's essentially treating the data just as you would treat it in so-called deterministic linkage. You either have it's a match or it's not a match, and you ignore the nuance that's built in to the actual estimation of a match weight. So that's also behind what I call this new algorithmic approach. So let's consider a simple case, as in this table. We've got 3 identifiers: age, postcode, and sex. And we want to assign to each of these attributes a weight W. So I've called it W1 if the age agrees. Substitute a birth date, if you like, for age. So if the 2 records where you're trying to establish whether they're the same person, if there's agreement on age, you will assign a weight W1 for that identifier for age. And if there's no agreement, you just assign a 0. I'm going to talk about an elaboration of this in a minute. For postcode, again, the same thing. If there's agreement, you assign a weight of W2. For sex, if there's agreement, you assign a weight of W3. And then the total weight or score for that pair, that candidate pair of records, one from one file and one from another file, is simply the sum of those weights. So, for example, in that last column, a pair that agrees on age, does not agree on postcode, agrees on sex, will be given an overall score of W1 plus 0 plus W3. Okay, and the real assumption behind this is that these weights you assign are all reflections of a common underlying scale, if you like, propensity to be a match. And what you would like is for the case where age, postcode, and sex all agree, that you would want to treat typically in any system as a match, because that's all the information you have. And where they disagree on everything, so zeros everywhere, then that's a non-match. So anyway, you can fix the ends of this scale. So W1 plus W2 plus W3, if you have a pair with that overall score, you would fix that, let's say, to be 1, represent complete agreement, and for a pair that has 0, but everything disagrees, you'd fix that as 0. So the statistical issue, James refers to this as a variant of correspondence analysis, and you can read about it if you're interested in the article, is to take the data where you've got a whole lot of candidate matches. So if you've got 1,000 individuals in one file and 2,000 candidate individuals in another, not all of whom will be matches, then the 1,000 by 2,000, okay, 2 million possible pairs of those, 1,000 will be true matches, the rest won't. You take those data, you look at the agreement relationships for each of those, and that allows you to estimate these individual weights. So I won't go into that, but what you're doing is you're trying to estimate this assumed underlying propensity to be a match. And later on, I'm going to be talking about how you then take that into account when you're doing some kind of data analysis. But note also, this is a very simple example. It may be that we've got several variables, age might be one, where it's not either you agree or you don't agree. You may have a degree of agreement, so that if age is to within the nearest month, you might say that's full agreement, but if it's only to within the nearest year, then that's partial agreement. It's not disagreement, it's a partial agreement because of the way in which age might occur. So what you would want to do is to have measures of partial agreement there. And again, I'm not going to go into that, but the data, rather than confronting you as a series of does the age agree or not agree, does the postcode agree or not agree, will confront you with a series of possibly partial agreements. It agrees 0.9, it agrees 0.6. And certainly with an identifier such as name, that's particularly important because names can be misspelled. The same name, John, Johnny, Smythe, Smith, may in fact be referring to the same person because they're recorded differently. They come out as different. And you would want to assign some kind of measure of agreement rather than just they agree or don't agree to that. So not just 0, 1, but some partial measure. And there are all kinds of systems, sound X, metaphonic systems and so on for doing that can be built in. And that in principle is not a problem as to the computational burden, but it's not a real problem in principle. So I've already said some of this. The first 2 bullet points are to give a no match for those 3, score of 0, complete match. We can fix it at 1 or 100 or anything you like, something convenient. And the scaling, what we call our scaling algorithm, as I said, assumes a single underlying dimension of agreement, and that we run through the data and we finish up with these weights, and that's the reference. It, we think, has 2 advantages. Firstly, it's much, much faster than any of the existing algorithms. James didn't mention it, but there are some, in the literature, there's some Bayesian-based algorithms for actually calculating or estimating match probabilities, but they're impossibly slow and they're not really feasible, but there is some literature on that. The Fellegi Sunter is an iterative algorithm which can be very slow with large data sets. This algorithm is at least an order of magnitude faster, and that's actually rather important when you're dealing with large data sets. And we think it's intuitively more appealing than existing methods, since the criterion that we're optimizing of agreement of this underlying scale is a rather sensible one, whereas the Fellegi Sunter one is, well, first of all, the statistical model doesn't make a great deal of sense, but it's also very difficult to feel intuitively that this is a sensible thing to do. And of course, it doesn't rely on any of the independence assumptions that either James or myself have referred to. So, okay, a little bit about some of the further research before we go back to some of the other issues that we're doing based on the use of this algorithm, which I have to say makes this research feasible because it's fast enough to do some of the complex computing that one needs to do, is to extend it not just to linking of two files, but to multiple files, if you like, creating population spines where you've got individuals that you're all the time wanting to link or update with new data sets, and calculate these weights that are attached through each time you do that. So you're carrying all these weights that you estimated from the previous linkage stage right through and storing them all the time so you can later use them for analysis. I've also mentioned the efficiency, and I'm going to be talking a little bit, James already mentioned this, about the imputation algorithms for when we do data analysis. So, James, back to you.
Okay, I'm going to introduce now something that is very new. So this is something that Harvey and I are still debating quite heatedly, so it's not by any means a done deal. But I'm about to be submitting it for, resubmitting it to IJPDS shortly. So one thing that both Fellegi Sunter and Harvey's scaling algorithm have in common is that they are ways of producing scores based on observed agreement, and these can be applied to any single candidate pair of records, even patterns of agreement that don't exist in your data, just hypothetical patterns of agreement. You can still calculate a probabilistic match weight or a scaling score from Harvey's technique for any hypothetical pattern of agreement. But we can also think about match probabilities as being proportions. So the proportion of a group of candidate pairs that are matches, given their pattern of agreement. So a whole lot of candidate links that share the same pattern of agreement or similar patterns of agreement. And the value in this, thinking about them as proportions, is that proportions of any group can be broken down into proportions of subgroups, and proportions of subgroups can be aggregated up into proportions of groups. So, for example, the proportion of pairs that we observe agreement in can be broken up into the proportions of matches that we observe agreement in and the proportions of non-matches that we observe agreement in, although these are things that we can't observe directly. But if we can estimate those two proportions and combine them with the proportion of agreement that we do observe, then we combine these three proportions, one observed and two estimated proportions, to give you a match probability or a matched proportion. So, or a precision estimate, what proportion of a group of candidate links are matches. And so what I'm going to present now is based entirely on this these inviolable relationships between proportions. So the motivating example was linkage of a disease register to hospital episodes, which contained a diagnosis codes for that disease. So disease detection rates are likely to be imperfect in both of these files, so both in the register and in the hospital episodes. And there's this question of, we could use the diagnosis codes as a matching variable, so to make the people, the hospital episode records that had diagnoses more likely to link to the disease register, or we could use it as a validation tool, and an imperfect validation tool, because we can't be confident that diagnoses have all been recorded in the hospital data. So this led me to ask the question, under what conditions can one matching variable be used as a valid indicator of precision in the other matching variables? And the answer that I came to for that is when that one matching variable is independent of the other matching variables among both matches and among non-matches. And if this condition holds, then your best estimate of of the proportion of agreement among matches in that group is the proportion of agreement among matches in general. And the same for the U values, the proportion of agreement among non-matches. So if we take one matching variable and then group all the candidate lengths according to their pattern of agreement over the other matching variables, and if our one matching variable is independent of those others, then we can take the M value and the U value that for our one independent matching variable within any of the groups defined by their agreement over the other matching variables, plot them on this axis. So those provide our limits of 0% and 100%. And the level of agreement that we observe is on our one independent matching variable is our match probability. So in sort of plain English, the more the records in that group look like matches, the higher the match probability, and the more they look like non-matches, the lower the match probability. Algebraically, that's just this proportion. That's just sort of this difference between these two proportions divided by the total difference between the proportions that are the M and U value. So now what we have is an estimate of precision, ignoring one of our matching variables. But from this point, we can actually break that group up into the variables that agree on our independent variable and the variables that, the candidate lengths that agree on our independent matching variable and those that disagree on it. And so we're sort of reintroducing our one independent matching variable, and we can express those match probabilities in terms of the same three parameters. So the observed agreement on the independent matching variable and the M and U values for that matching variable. These are sort of horrible fractions, but they're based on they're just these same three proportions. They're just combinations of those same three proportions re-expressed. And so we're sort of aggregating back up to our target parameter, the match probability. So the key points from this were that the proportion of matches within any group of records can be estimated by combining these three proportions. And if any one matching variable is independent of the others, then you can consistently estimate the match probabilities or match proportions. But this is all using proportions. And so these are group statistics that depend on group size. And so you need to have a certain minimum number of candidate lengths for this to provide useful estimates of match probabilities. And just as a rough rule of thumb, that I think that's about 100 candidate lengths. Then we'll provide a reasonably consistent estimate of what proportion of those are matches using this approach. Smaller groups, so patterns of agreement that don't have many candidate lengths, they can be pooled, or estimates for, or perhaps estimates for those smaller groups can be modeled or extrapolated from the estimates for large groups. Why do this? So it provides, given that one independence condition holds, consistent estimates of actual match probabilities. Makes no assumptions at all about independence of other matching variables, and you don't even have to explicitly accommodate them. But it does rely critically on this one independence condition. Readily accommodates missing values in all of the other matching variables. You can estimate the match probabilities for the patterns that have missing values in the other matching variables. That's not a problem. And it's computationally trivial. So we're going to skip pretty quickly over these two ideas about analysis of linked data now, given the time. Basically, it comes down to there being sort of three options for how you go about analysis of linked data. There's what we currently do, usually, which is ignore linkage, error, and uncertainty. there's what a lot of us think about doing, but is rarely done, which is to estimate the error rates and adjust for them analytically, using either quantitative bias analysis or sensitivity analysis. And then there's what Harvey would really like us to be doing, which is addressing the uncertainty, not just the error, but the level of uncertainty around it using imputation-based analysis. So I spent a lot of time recently thinking about linkage error and how linkage error leads to bias. And it's really complicated. This is one of the reasons that we don't do anything about it, is that depending on the study design, linkage error can lead to missing data, it can lead to misclassification and measurement error, it can lead to selection bias, it can lead to double counting and undercounting, and it can reduce your statistical power. And so if it does all of these, if it can do all of these different things, then how is anyone meant to know what it's doing in their analysis? And so there's some examples here of how a missed link to a register of deaths, depending on the study design, could lead to misclassification of death status, which leads to what epidemiologists call information bias. It could lead to missing data about cause of death. It could lead to erroneous inclusion of dead people in your analysis that's only meant to include living people. And it can, or it could it could lead to somebody's records being split and then being counted twice, once as being dead and once as being alive. A false link, on the other hand, between two hospital admissions could lead to two people's records being merged into one, and then leading to sort of undercounting, as well as potential misclassification of these people as being readmitted when in fact neither of them were readmitted. And so how do we know what the implications are for analysis? Well, so Katie Harron and I spent a long time testing these out on data linkage students, trying to work out all the different possible study designs that are out there using linked data. And what we worked at is that for any combination of two files, there are 3 different possible set structures and 11 different regions of interest, so sampling frames that different analyses might draw from these 3 set structures. And then there's a 12th sort of linkage structure for any time that one or both files need to be deduplicated or internally linked. And that by by understanding which of these 12 fundamental structures are at play, and sometimes it's combinations of these, especially if you're dealing with more than 2 files, by understanding those, you can identify what the implications of linkage error are in terms of conventional biases, which can then facilitate quantitative bias analysis and or statistical sensitivity analysis. Now I'm going to hand back over to Harvey to talk about imputation.
Okay, thanks, James. Well, I already said something about this, and James has dwelt on it in some detail. And there's now literature that says if you insist on ignoring the uncertainty, you can come to quite inappropriate conclusions. You could even reverse inferences about differences between groups. So in many situations, this is actually rather important. Let me press on, as time is going. The primary kind of, I think, insight into this is that you can think of the whole linkage problem essentially as a missing data issue. So we're trying to link 2 files, a primary file A and a file B. And the point about file B is that essentially it contains the same individuals in file A, but it contains information on variables that you don't have in file A. So what you would like to finish up with is an enhanced version of file A, which initially, for the variables that are in file B, has a set of missing values. What you want to do is to bring across those values from file B. The way you do it is via record linkage, but that's an incidental. That's just a way of doing it. Essentially, what you've got is a missing data problem. You want to fill in those missing data. Okay, so I talked about a primary file and a secondary file. So let me just illustrate this with a simple example. Here is the primary file, okay, and I've got 4 records, 4 rows here, and I've got 3 variables. Doesn't matter what they are. And each of these is observed in the first record, my file, also in the second record, also in the third record. In the fourth record, I actually happen to have missing data already in file A on that. Never mind. But initially, these variables that I'd like to kind of bring in to my primary file because I want them in my analysis are all missing. They're all zeros initially. So the research problem is to change the zeros to the x's, the noughts to the x's. And I hope you can see, and I'll illustrate in a minute, this is a particular case of missing data, and modern ways of handling missing data are essentially based on a Bayesian model that I will attempt to describe a little bit. So let's now do some matching. Let's now match on some identifiers like age, sex, and so on. And let's assume that in rows 2 to 4, records 2 to 4, all our variables, all our identifiers agree. So we have deterministic matches. Okay, we have perfect agreement that identifies these, and we know which records are the correct ones to bring across. And so you see immediately that we have X's in the enhanced file after linkage for those 2. In this one, I'm going to assume row 1, we don't have any plausible matches. So nothing is brought across. And in row 4, again, it's like rows 2 and 3, but we happen to bring across a real bit of missing data there as well, as it happens. So this record, this individual, is very prone to have missing data. But now let's look at this matrix. We've got 4 individuals, and we've got 5 variables, and we've got missing data all over the place in general. But we have some individuals that have complete data. And this is a classical missing data problem. We know exactly how to deal with this. This is dealt with, and there's a long literature on this going back a good 30 years by Bayesian-based imputation methods, the best known of which is so-called multiple imputation, which is implemented in a number of software packages. And in many situations, this sort of thing is what we finish up with. And we need to do no more. We need to stop. We can stop there. We don't need to worry about imperfect matches, these weights lying between 0 and 1 and so on. Forget about them. Even if 10 or 15 or maybe 20% can't be identified in the deterministic sense of all the identifiers agreeing. Nevertheless, under certain assumptions, you don't need to do anything else. You're going to get consistent parameter estimates out of any old statistical model you want to fit, a factor analysis model, a regression model, simply by going through the well-known imputation-based techniques. Now, the condition for this is that the missingness is at random. And that's, of course, a condition for all imputation methods. And one of the things that you might want to do in this process is to use other variables, which you don't particularly want to analyze, but which may be associated with the propensity to be missing. They may be in either set, A or B, but they can be conditioned on when you're doing the imputation. So
Auxiliary.
they're called auxiliary variables very often. If you regard the problem in this way, and for statistical purposes, this is sufficient, you may just stop there, forget about all the apparatus, Fellegi Sunter and so on, just do a deterministic method where you take complete agreement as being known, complete non-agreement as being unknown, and hey presto, away you go, making sure you're happy about the missing at random assumption. And I would suspect, although we don't have much data yet, not much exposure, that actually in most cases, that's fine. You get away with it. And if you're dealing with big data sets, you're losing efficiency to some extent. But, if you're dealing with a record file of 1 million, so what? You get 80% efficiency. You can still do the analysis you want. And in many ways, that's it. Full stop, finish, go home, and you spend a lot more time. However, that won't always be the case. And certainly, you want some procedures for handling the uncertainty, the uncertain matters. So now we go back to either the method that James described, his method, which we're still debating, or the scaling method, or even the Fellegi Sunter. Doesn't really matter very much. You finish up with a set of weights, or match probabilities, if you think you can do that, and you treat those weights as measures of uncertainty. You can rescale them to go from 0 to 1 and treat them as probabilities. And within a standard Bayesian framework, those probabilities will enter the imputation procedure as additional information about the likelihood that it's a correct match. And that then enhances the whole imputation process. So I'm not going to go into detail, but that's essentially what you're doing. You run the whole thing within that Bayesian framework. And the really nice thing about that is you're not just going to use those weights, which you've rescaled to think of as probabilities, but you're actually, for each one of those candidate values or records that you want to bring across, and there may be as many as 5 or 10 of those that are reasonable to think of, you will have the potential values of these. And those potential values also give you information, because if those potential values that you want to fill in here are a long way, in some statistical sense, from the values you would get just by conditioning on the things you do know, which are the things in the original file A, which is how imputation works, then that counts against them. So you're not only using the identifier information, you're actually using what is often called the payload information to enhance the data. And and that's what is meant by carrying through the probability into the analysis, because what the imputation procedure gives you is a measure of that uncertainty that then gets incorporated in the subsequent statistical modeling. So multiple imputation, that's included in what are known as Rubin's rules, and in what we developed a few years ago, what we call fully Bayesian imputation, that's also included inherently in the way you do the analysis. And to my mind, this is the crucial issue. It's not how you calculate weights, it's important, but you can do it in all sorts of different ways. You can do sensitivity analysis, you do it different ways. The important thing is you take that uncertainty and you carry it through to the analysis. And that's one of the important messages I would really like to get across. So this is the basic original paper that myself and Katie Harron and Angie Wade published a few years ago. And I recommend, if you're interested, you read that, and we are, I have to say, we are developing software. We already have software for the scaling algorithm, and we're developing software based in R to do this bit of it very efficiently. So, back to you.
As a quick summary, the probabilistic linkage step is sort of pretty computationally challenging, but these ideas that were presented today offer some promise of the simpler and potentially more objective approaches to estimating match rates or match probabilities, and particularly that offer opportunities to overcome the independence assumption. But our sort of main point is that the potential value of probabilistic linkage for capturing information about uncertainty is not being realized in analysis of linked data. And for that, so we really need to be retaining information about uncertain links and stop treating probabilistic linkage in this deterministic way. And lastly, there are a lot of lessons that can be learned about analysis of linked data from analysis of missing data. I think that in terms of analysis of linked data, we're probably currently, 30, 40 years behind the methodological development in analysis of linked data, and they really are very closely related topics. Is there anything you wanted to add to?
No, thank you, James. I think we covered what we wanted to say, so we can go over to a chat now.
Thank you, James and Harvey, for your excellent presentation. Lots of details for people, and also thank you for the references so people can follow up. I have a couple of questions from the audience. The first one is, again, thank you for the great talk. I'm wondering what analysis softwares, more specifically, which packages in R would you recommend for probabilistic linkage?
Yeah, I'm afraid I'm a data programmer, so I haven't used R for probabilistic linkage. I think there's one large package that contains sort of all of the possible things you could ever want to do in linkage in R.
Well, I'm not sure I'd recommend any. I have had experience with one or two. They're very slow. They're not properly optimized. In fact, if you want to kind of have an algorithm as fast, you don't write it in R. You write it in a much lower level language like C++, or you mix the two in some way. So all I can say is that we currently have a project, a 3-year project, which is about to start. And one of our commitments is to develop efficient software that will be available using R, but it will be optimized by using much lower level code where necessary. So we already have one working version. If you want to email me, I can send you a copy which you use at your own risk, because it hasn't really been properly tested yet, but we are committed to developing that software.
My comment on that would also be to consider coding it up yourself. The computational steps in probabilistic linkage are fairly simple, and once you understand the process, it's not difficult to program in almost any software. Programming it efficiently is a different matter, but I've seen plenty of cases of probabilistic linkage done badly where they've taken off-the-shelf packages and used them without understanding what was going on under the hood, and have implemented things which really didn't make a lot of sense.
If you want a quick method, there's no something called Link Plus is quite good. But I'm not recommending it. I'm just saying it's out there if you want to try it.
There's also software being developed by the Centre for Data Linkage at Curtin University in Western Australia that I'd recommend looking into.
Thanks very much for your response. And another question, is probabilistic linkage the same as fuzzy linkage?
So one of the big issues with the literature on linkage in general and probabilistic linkage in particular is how many different terms are bandied around to mean so many different things. So I think of fuzzy linkage as being simply any linkage that doesn't require full perfect agreement on either one particular matching variable or on all the matching variables. And that's how it's usually used in both of those terms. So sometimes some people have equated probabilistic linkage with fuzzy linkage, but I think they're not the same thing. I think about probabilistic linkage as being linkage that tries to get some handle on the uncertainty associated with a candidate link or a set of candidate links. So some idea of the match probability, or even if it's just a score that correlates with match probabilities. Whereas, and one of the things that probabilistic comparison techniques do better than deterministic techniques is allowing for partial agreement, which is what, to me, fuzzy agreement means. It's just partial agreement. So it's not. It doesn't have to be full agreement, and it can allow for those approximate measures of agreement.
I think fuzzy linkage may in some way be a better term, probabilistic linkage, because certainly the Fellegi Sunter method I pointed out doesn't really satisfy a proper probabilistic model. So fuzzy linkage, I think, is probably a better term. As James says, it implies something between 0 and 1.
So they're similar in that way, yeah.
Thanks a lot for your responses. Really appreciate it. So a number of thank yous for you for presenting today and the great teaching that was offered. So, and I think everyone has your contact information through our email, your websites and things. So thank you for providing that. And also thank you for the number of references you provided for follow-up for people to learn more, and for taking the time today to present. I don't think we have any further questions, and we're probably just out of time now as well. For everyone who's still online, we will be providing this recorded presentation online, and I will send out an email to everyone when it's available. So thanks again, James and Harvey, for presenting, and look forward to further discussions.
Thank you, Anne. I should just throw up my acknowledgements before we go, which we put a paid up. Thank you, everyone.
Goodbye.
All right, thank you.